Welcome to another member seminar. It's great pleasure today to have Kenji Fukaya giving our second senior talk of the BIMSA member seminar. Kenji is one of the true world experts of symplectic geometry. It's an honor, so please.
Thank you very much for introductions. So I want to talk functoriality in Lagrangian Floer theory and how it appears in various related fields of mathematics. So that's my theme. And I think I talked about functoriality in BIMSA also a few years ago, but I don't want to afraid any overlaps because this is a kind of broad audience. So first I want to explain what I mean by functoriality in Lagrangian Floer theory. So the question is, it's a kind of old question. What is a category of symplectic manifolds? I think you know that the symplectic manifold is a pair of manifold X with omega. Omega is two form. The omega is 0 and omega n never 0, right? So this is what the symplectic manifold is. And if you see the many similar notions like a smooth manifold or complex manifold, people know what is a morphism between them. The manifold between smooth manifold is just a smooth map. And the morphism between complex manifold is a smooth map whose differential is complex linear. And if you want to go to symplectic world, you want to try to define the notion of morphism. And the most obvious, so this is a complex manifold, right? So in category of complex manifold, the object is a complex manifold. The manifold which has which locally can be identified to the complex vector open set in complex vector space, and the coordinate change is biholomorphic. And morphism is just a holomorphic map between two complex manifolds. And the category of complex manifold is expanded to including many things with somehow singular object, category of schemes or even stacks, blah, blah, blah. And the category of smooth manifold also I said that is very established notions. So now, what is the category of simplex manifold? Object is obviously a simplex manifold. And the main difficulty is to define the notion, the morphism. Why is it's not so easy? So the obvious, you want to consider somehow obvious choice. If you have a map from M to N, and M has a symplectic form omega, N has a symplectic form N, then you want to see that this looks like natural conditions for a map which preserves the symplectic structure. This is the first candidate, but one bad thing is that this condition automatically implies that the dimension of M is not greater than dimension of N, because the rank of symplectic form is non-degenerate unsymmetric two form of the tangent space. And if you put back the unsymmetric two form, they have another unsymmetric two form, but the rank does not grow. So this condition just implies that the dimension of N is not greater than dimension of M. So it's a bit not so much symmetric. For complex manifold, you have something like M cross N to M, or embedding and projection. Both are holomorphic map, but symplectic world, it is not allowed if you just define it in this way. So the most natural, the good symplectic diffeomorphism, the good map you have obtained here is mostly a symplectic diffeomorphism. So the categorical framework does not work so naturally. And for these issues, Alan Weinstein proposed many years ago, more than 40 or 50 years ago, I suppose, what is a good notion of symplectic morphism? That is a Lagrangian submanifold of the direct product of minus M cross M. So what is Lagrangian submanifold? So if you consider this M cross N, so what does this mean? So this guy, M has a symplectic form omega M, and N has a symplectic form omega N. If you put back omega m to this m, and you take minus, and you take omega, put back to the projection m. It is a two form on this product. And you see that this is a non-degenerate. First of all, this is a closed two form because the pullback of the closed two form is closed. And it is a non-degenerate in both directions. So it is a symplectic form. And what is so if you have this x omega, then L, so if x is 2 n dimensions, is a Lagrangian submanifold if and only if dimension of L is half of dimension of x, and the symplectic form vanishes. And Weinstein's proposal is that if, this morphism from M to N should be a Lagrangian submanifold L of minus M cross N. And there are various reasons. Later on, I will explain much more examples how this kind of morphism exists. And actually, there are rich examples of this kind of morphism. That's why this is interesting. But in the simplest case, the following: you have a phi from M to N, symplectic diffeomorphism. Then we can just take L is a set of x, phi x. So this is a subset of M cross N. And you can easily see that the fact that this, so this is minus, and so these two forms just put back the same form. So if you take the minus sign, then you get 0. So the graph of symplectic diffeomorphism is a Lagrangian submanifold. So that's one instance why this is natural. And I just want to mention only another instance. It's a following. So you have a M1, sorry, M2, and you have a L1. So you have this minus M1 cross M2 and L1, 2. And you have L3, M3, and minus M2 cross M3 contain L1, L2, 3. So the natural thing you want to do for the morphism is you want to compose the morphism. Then the composition in this case is actually nicely obtained. You take fiber product, and then this goes to M1 plus M3. So you have this two projections to M2, and you take a fiber product on M2. Then you have this fiber product spaces, and it is a bit kind of some kind of exercise that if everything is transversal, this fiber product is actually a Lagrangian submanifold of M1 cross M3. So you can actually compose Lagrangian correspondences. So I just want to explain two examples. It generalizes the notion of symplectic diffeomorphism, and also you can always compose Lagrangian correspondence. You have another example, so that Lagrangian correspondence is a good candidate of the morphism. So this is a proposal of Einstein, and this the set of all a pair of L1, 2 and L2, 3, which goes to the same point in M2. This means that you have a set of xy here, so that pi M2 x is equal to pi M2 y. It's a subset of the direct product. Okay, so now this is compositions. So now, so this kind of proposal is done much before. Kind of Gromov introduced the homological curve and kind of start this global symplectic geometry. It's 50s or 60s, but then after this global symplectic geometry is getting more and more works. Then there is one issue which people are not so much happy is Gromov-Witten theory is not functorial with respect to this morphism. So you recall that what's nice about homology theory? Homology theory, you have a M and N spaces, and you have a morphism is just a smooth map. Then you have a homology group of N. Then they have it put back to the homology group of M. So the homology group is a covariant functor from the space of manifold to the space of commutative ring, or more kind of just continuous spaces. And if you see about the sheaf theory, there are sheaf cohomology. So you can put back sheaf, and the sheaf cohomology has some kind of functoriality. It's more delicate than homology. So there are a lot of functoriality for this complex geometry and also in topology. However, it is remarked at the very beginning of the story. So Gromov-Witten theory is something like a counts something like a map from S2 or Riemann surface to M. And the first case which we can make some nice thing with something called the quantum cohomology. Quantum cohomology is the deformation of the ring structure of symplectic manifold, so that you have some S2, homological S2 on M, and using this existence of homological S2, you deform the ring structure, original ring structure, the cohomology, what is called a quantum cohomology. Then it is observed from the very beginning. Quantum cohomology is not functorial in the usual sense. So for the algebraic geometers, they first try to think with that whether this quantum cohomology is functorial for holomorphic map. So you have two Kahler manifold, two complex manifold, projective variety, then holomorphic map. Then it induces. So you have, of course, you have a map between cohomology, but you cannot expect that quantum cohomology is a ring homomorphism. There are many examples. So in that sense, quantum cohomology is not functorial. And so far, nobody has a very good proposal to make it functorial. I want to understand it, but it's still very mysterious problem. So that's one bad point on this Witten theory of quantum cohomology. However, one good thing is what I want to call the Lagrangian flare theory is actually functorial with respect to this Weinstein's proposed category. So it is more closer to the homology theory or homology theory. In the sense, you can associate symplectic manifold to something which can come from Lagrangian flare theory, and this association works nicely functorially with respect to this Weinstein's proposed notion of morphisms. So what it is? So I just want to state a theorem. It's a bit. I need to explain many things about what this theorem means, but just state it. So there is something called a two-functor from Weinstein's category of symplectic manifold to the category of all infinity categories. So what is Weinstein's category of symplectic manifold? The morphism is symplectic manifold, and I don't know, object is symplectic manifold. Morphism is a Lagrangian correspondence. So that's a geometric category. And here have a algebraic category that is called the category of all infinity categories. So category of a category is a bit more kind of abstract things. But if you say that let me forget this infinity category. But category of a category is actually something called a two category. So what is category of a category? Object of a category of a category is category. Object is a category. And morphism between one category to the other category is something called a functor. So you know the functor here, but so that is morphism is called the one functor. So you have two morphism, say. So you have a you have a category C1 and C2, and you have a two functor. Then there is something like natural transformations between two functors. Actually, you have a given two categories C1 and C2. You have another category, so that its object is a functor from one to the other. The morphism is a natural transformation between them. So in that sense, you have a kind of object, one morphism and two morphism. Object is a category, and the morphism is a functor. Two morphism is a natural transformations. So this claim says that so it's a bit more complicated. Category of all infinity categories. Infinity category is some variant of categories, where in the category theory, one important thing is that the associativity of composition of functor is one of the basic property. And in infinity category, this associativity not strictly holds, but it's up to some homotopy, and you can go this homotopy after infinity levels. So you have some version of the category that's called the infinity category, and there is some algebraic framework, and it is not so easy, and people still complain. But category of all infinity category is something like some kind of two category, and the name should be infinity two category, blah blah blah, blah or something, or maybe infinity category. So that is the algebraic part of the story. So geometric part of the story is Weinstein category of symplectic manifold, but actually one can make it into two category because so object is a Lagrangian submanifold with direct product. And between two Lagrangian submanifold, there is something called the Floer homology. So if you have a two Lagrangian submanifold in a symplectic manifold, under this Floer, they find some homology theory, which is the abelian group. And so we have a two category, so that the object is a symplectic manifold. One morphism is a Lagrangian correspondence, and two morphism between two, that is a Floer homology between two Lagrangian correspondences. So you have a two categories. One is a category of all infinity category, and the other is a category of all symplectic manifold enhanced using this Floer homology. And the theorem says that there is an infinity functor between them. And this kind of, I try to do this kind of things in the 90s. And I think around 2000, Wilhelm and Woodward start working on it and get some first non-trivial cases that this story works. Together with C.T. Mao, they construct some infinity of things. And Wilhelm and Botman continued this research so that they remove this rather restrictive assumptions Wilhelm, Woodward, and Mao did. And there is a study by Yankee Lekiri and Max Lipiansky. They do a similar thing, but from a different method. And I think in 2017, I think I wrote a papers, and I think this one largely now established as the theorems. Unfortunately, 7 years paper is still under referee. It's 300 somethings, and there are 4 referees who start one. The 3 referees are satisfied, but the fourth one takes 3 years and do not reply yet. So, but I believe it is correct, and so okay. So now, I just want to hear a few words. What is this this general theory? So the first of all, for the object symplectic manifold, one need to associate something called the infinity category, and that's called actually Fukaya category by Kontsevich. So what is this infinity category? Its object is a Lagrangian submanifold of the symplectic manifold. So it's a half-dimensional submanifold of which symplectic form vanishes. But it is not only case. One needs some additional data, B, called the bounding cochain. This looks a bit kind of artificial. And at the beginning, we or several people do not like it. But actually, this bounding cochain is very important role, and it's kind of main key player. So B is something like a deformations of a drum complex, or something like a deform flat kind of flat bundles somehow. So it's a kind of extra data. Basically, ortho-dimensional cohomology classes. And we have a 2 Lagrangian submanifold with bounding cochain. And then we have a Floer chain complex. So what Floer did is just Floer studied. So Floer studied this Lagrangian submanifold. And then you have this L1, and you have L2. Then you have a P. So Floer chain complex is some. So yeah, I think in Floer's case, he used D2, but finally, it is natural to take something called a Novikov ring. So you have a free module whose basis is this intersection point. There are much delicate story because the number of intersection could be infinite. So you have to do some perturbation business. And this is a chain complex. You have to define boundary operator. Floer's original definition is just to count it, this kind of disk. But actually, I need to use bounding cochains and this modify it so that you get nice chain complex. But that's the story. And then composition of the higher composition is to count pseudo-harmonic polygons. So what is pseudo-harmonic polygons? So you have this several L's. Right, so L0, L1, L2, L3, and P0, P1, P2, P3, P4. Then we can just count homomorphic map, which is a rectangle and whose boundary is a union of these Lagrangians. And this is something called I think M3, P0, P1, P2, and its coefficient in P4 something. So I don't want to explain any detail, but counter this kind of things give some compositions and its generalizations so that you have a nice category. So that's a general story. And this story itself, I started in the 90s, and it takes maybe 20 or 30 years and to write it up. And maybe some people still complain, but we wrote several hundreds or maybe even 1,000 pages to write it. But it now gives this MPT category. And also Akaho-Joyce, because we need to include immense Lagrangians. And the reason we need to include immense Lagrangian is very important, because if you have a two Lagrangian correspondence, which is realized by embedded Lagrangian submanifold, but you compose it, you take this fiber product, then generically you get only immersed Lagrangians. So if you stay in a world of embedded Lagrangians, you can never, there are some cases you cannot compose two morphisms. And I think in category theory, it seems likely, I think we have to do it as general as possible, right? For individual calculations or some examples, you can put some conditions and you can work in this kind of thing. But category theory, one good thing in category theory is that you can do everything, right? Kind of, and if you have a categories and you fix in some world, then everything should be defined in the world. So any restriction is not appropriate. So the category business to enhance the story to imagine case is rather inevitable. That's what Akaho-Joyce did. Okay, anyway, so now, what's the morphism part? So what is the morphism part? So Lagrangian submanifold of minus m cross n is an morphism. Actually, in our versions, this Lagrangian submanifold should come with bounding cochain. So the pair is a morphism. So now, so now this theory says that it should give a functor. So W is for Wilhelm-Woodward's WL12, which is an infinity category associated to M to infinity category associated to M. And this is something like this is already known. It's by Weinstein himself. So if you have a M, Lagrangian submanifold of M, then we take again this fiber product. This fiber product, if you project to second factor, you can see that it is a Lagrangian submanifold of M. So for the object, you can again take this geometric fiber product, how this one object go to the other object. But of course, so this is, I think, already Weinstein knows. So but what we have to do is just to how this full story matches with Floer homology. Especially, Floer homology is based on a rather delicate object, counting of homomorphic disks. So it's a kind of highly nonlinear PD appears. And it is something very surprising that this kind of construction completely match with this construction of the Floer homology. So that all these operations coming from polygons just become consistent. So you do this one object part, then all the Floer homology just maps by this functor, and all the operations, infinity operation come with infinitely many operations with infinitely many relations, and they completely consistent to give this infinity functor. So that is the second part of the story. And of course, you have to prove something else. For example, this one should be also functorial. So if you compose two Lagrangian correspondence, you have another Lagrangian correspondence, then it should be compatible with this functorial. So everything should be functorial, and that's I think now proved. So you have this full functor, full constructions. So now, but then I just want, before going further, I want to mention one non-trivial point, I think, which kind of prevent Wilhelm-Woodward to go beyond some case, but they go monotone. It's this case, is this point. If you have a L12 and Lm, both has a bounding cochains. Having a bounding cochain is basically equivalent. You can define Floer homology. So it's what we call unobstructed. I mean, me and Ono call this notion of unobstructed Lagrangians. So if L12 and Lm are nice Lagrangian in that case, then if you take this fiber product, that should be the morphism. That should go to the Lagrangian submanifold of M2. And we proved that L12, Lm unobstructed implies Ln is unobstructed. And this is actually a key statement. And once we can prove it, then all this functoriality goes through. Okay, now this is the story. So now the rest of my talk is just how to explain these things related to various mathematics. So first thing should be something like a homological mirror symmetry. So this is they go back to Kontsevich. And what Kontsevich proposes is that if a symplectic manifold M, then we can associate something called a mirror. It's a complex manifold. So homological mirror symmetry, one side has only symplectic and the other side has only complex structure. Then the object on symplectic side is a Lagrangian submanifold L. And then the object in the complex side is a sheaf or a chain complex of sheaves on this complex manifold. And what Kontsevich conjecture is that Floer homology on the left-hand side correspond to sheaf homology on the right-hand side, and everything should be functorial. And then it should be more functorial. It means that the left-hand side and right-hand side is both now both is a category. So you have a Lagrangian correspondence between symplectic manifold and Lagrangian, and also a holomorphic map for a bit more complex correspondence between complex manifold. And then this two functor, which goes to this Floer theory or sheaf theory or Lagrangian Floer theory, corresponds. And that is basically expected at a very early stage. So what is expected to be a mirror to Lagrangian correspondence, and it is expected to be a Fourier-Mukai transformations. It is a thing like this. I think Mukai studied this kind of things to study several interesting property of sheaves on K3 surface or tori. So what is this? So suppose we fix some sheaf on a direct product. Then if you have a sheaf on M, then we put back to this direct product, tensor F, and push out to N. Of course, you have to do everything in so-called derived world. So the sheaf on a direct product gives a functor from derived category of coherent sheaf of M to derived category sheaf of M. That's called a Fourier-Mukai transformations. And it is almost immediate from the definition of homological mirror symmetry. Lagrangian correspondence functor. For the Lagrangian correspondence, which gives a functor between two infinity category in Lagrangian Floer theory, that exactly corresponds by this Kontsevich homological mirror symmetry to this Fourier-Mukai transform. That I think maybe most of the workers in most of the people in homological mirror symmetry works knows. But since this correspondence issue in Lagrangian side is not so much well developed, known at this stage, so I don't know how much people proved this correspondence in general. I think this Ivan Smith and Abuzai use this kind of things to prove some version of homological mirror symmetry on T2 cross T2, but that's a primitive case. I think the coincidence is hold in great generality, but I think nobody yet tried down such a kind of things.
Can I quickly ask you something? The reason you have put pi n lower Schrick is because you're tensoring with the relative dualizing of some sort? It's not pi lower star? Pi n lower star?
I think fiber is compact, right? So it doesn't make so much sense. Maybe it's better just a derived is more emphasized.
I see. And then in these examples that you mentioned, what is the F, the Fourier-Mukai kernel?
Fourier-Mukai kernel is a mirror to L.
Mirror to L.
L is the Lagrangian submanifold of the product. So if you go to the mirror, there should be some
local system. Yeah. Okay.
So now I want to explain something very different. It's a more symplectic word. That's called the generating functions. So if you go back to this early word of Hamilton and Jacobi, there is a notion of generating functions. That's a method to cook up Lagrangian submanifold. So what it is, so the simplest example of Lagrangian submanifold in cotangent band is just a graph of closed exact one form, right? The graph of closed one form is a Lagrangian submanifold. And to obtain this closed one form, of course, you take functions and take its extra derivative with natural. So that's the easiest example. And the generating function is somewhat stabilized. So if this there's no y, just x, then this story is exactly this d of f. But if you increase this function f with extra m variables, then you consider the subset so that the y derivatives are completely zero. Then if you take this, so y derivative is always zero. And then if you take this map from xy to x df dx dx, This is a map to the cotangent bundle. And it is very classical. I don't know how much Hamilton knows, but at least Jacobi knows it very well, that this is a Lagrangian submanifold. And this is one typical example how to obtain Lagrangian submanifold in the case of cotangent bundle. And I want to write down one theorem. This Lagrangian submanifold with generating functions always has a bounding cochain. That's a theorem which I'm writing with Atiyah-Floer. And also, Floer homology is actually a Morse homology. And actually, this theorem has a long history. So I just wrote a lot of names, and Kontsevich, Viterbo, and there are a lot of people working on in the one-dimensional case, working on this Legendre nota kind of things. And the work in the dimension 2 is started. And but then why I talked it in this form is the following thing. So there is an observation which is also classical. It is written in Eliashberg Gromov's paper, but probably they don't even it's not their inventions. Maybe much earlier people. I don't know where Jacobi knows, but it's something like that. So you take this Rn cross M. Then you have this Rn. This is xy to x pi. Then you take something like a conormal bundle. It's a conormal bundle. It's a this is something called the Lagrangian submanifold. I don't want to explain because timing is a bit tight. So if you have any maps, if you take the direct product, you can define some notion of conormal bundle. You have a submanifold. The conormal bundle is a pair of the base space and the covector which vanishes on the tangent space, right? And you can define this kind of thing for this maps. And what we know is that if you take this graph of df here, and then this conormal bundle, let me write f. Then you take this df and this L, and this fiber product, and this is actually this generating functions. So this Lagrangian submanifold, which has a generating function, came from the graph of the exact one form by this particular Lagrangian correspondence. So this theorem is in a sense a corollary of the fact that unobstructedness is preserved by Lagrangian correspondence. But this example is rather rich example because in a world of knot theory, people studied this kind of things for a long time, and also generating function itself is a very important object in yeah. Okay. So now, our next example is something called a symplectic quotient. So suppose you have a symplectic manifold which has a group action of a compact group, and there is a notion called the moment map. So you have for example, the simplest example is A with Cn and the G is S1, which rotate. The moment map is just a square of the absolute value norm. And then using this moment map, you can take this symplectic quotient. If you are algebraic geometers, then the existence of moment map is somehow equivalent that this action extends to the homological action of the complexification of G. And then you take this quotient, and that coincides in a complex situation, so-called the GIT quotient. So now you have this notion of quotient. This is important because you just divide M by G. The quotient space rarely has no natural symplectic structure. But this symplectic quotient preserves this notion of symplectic structures. And this has a lot of histories. Or one history from this algebraic geometry, and the other is the symmetry of Hamiltonian systems, blah, blah, blah. And what is expected? I think, maybe Telemann give some explicit conjecture as the following. If you consider this Lagrange-Floer theory on M, but equivariantly of a G. So I don't want to explain what is the equivariant Floer homology, but you take the equivalent Floer homology of the above, then it is isomorphic to the Floer homology on the basis. So if you consider G equivalent to the above, then you can do this with the quotient space. And that's, I think it's called Telemann's conjectures. And there are many people who think about this kind of things. And then there are several works, many works based on so-called gauge schema model. It's some kind of a hybrid of pseudo-homological curve and gauge theory. And this gauge-Sigma model has a long history, and I think recently this Xu, Woodward, and Tian gave various important results, and they approach this kind of problems from this gauge-Sigma model. But there is another approach, because there is a natural Lagrangian correspondence from M to this symplectic quotient. So you have some Lagrangian submanifold, which is direct product of M and M minus quotient. And using this Lagrangian correspondence, we can cook up symplectic infinity functor. So the main thing is just after making one of them equivariant, we want to make it isomorphism. So that's an approach. I think it is different from gauge-Sigma model approach, but it's more kind of functorial things. And I think one of my students, Yao Xiao in Stony Brook, is studying this kind of things. First, she studies more on this equivariant for homology and blah, blah, blah. It doesn't, this story does not finish yet, but it is getting closer. And I think also there are some mathematicians in Hong Kong who recently wrote papers, Dung and those people. So now, next thing is something called the Atiyah-Floer type conjecture. So this is something like an infinite dimensional analog of this simple quotient constructions. So what is this kind of thing? So I explained it in this way. First, we take a two-dimensional manifold, and then a principally SO3 boundary on it, so that its second symmetric class is sigma. Then we consider space of all connections on this SO3 boundary. It is, of course, infinite dimensional spaces, and it is a affine space whose associated linear space is a set of SO3 real algebra valued, twisted, real algebra valued one form, twisted by this spaces. So you have a vector affine space, and G is an infinite group of gauge transformations. And so you have this picture. And this space of infinite dimensional thing has a natural simplex structures. And if you just try to imitate the construction of simplex quotient formally, then this simplex quotient is a flat space, moduli space of flat connections. Actually, it is a famous fact that the moment map in this setting is a curvature. So it's related to this curvature conditions. So now, what this theorem says that this G equivariant Lagrangian-Floer theory on this infinite dimensional space is some Floer homology on this moduli space of flat connections. And we can kind of regard this as a kind of relation between gauge theory and simplex geometry in the following way. So suppose you take this three manifold whose boundary is sigma. Then you just look this. Then you consider all connections on sigma which extend to xm. That is something like a half-dimensional conditions as usual. And you see that it's something like a consequence of Stokes' theorem. The set of all connections which extend to sigma m, the set of all connections on sigma which extend to m is a Lagrangian submanifold. That's basically Stokes' theorem. So now, what is it? So then if you have this, so you have this boundary m1 is the sigma is minus boundary m2. You have this two Lagrangian submanifold. And basically the issue is that the Lagrangian-Floer theory for this two Lagrangian submanifold, G equivariant Lagrangian-Floer theory on this pair of Lagrangians is related to the instanton Floer homology of three manifold, so that the M1 and M2 are glued on sigma. That's the one side. So you just try to imitate the story that the G equivariant Lagrangian-Floer theory on this infinite dimensional manifold is a gauge theory instanton Floer homology. And then the Lagrangian-Floer theory on the simplex quotient, that's a space of flat connections. It's a usual Lagrangian-Floer theory, and they coincide. And that's called the Atiyah-Floer conjecture. And with Arikaba Diamond and Max Lipinski, we are doing this kind of things. And actually, this theory also has a kind of two different approach. One is using more analysis, like Xu, Tian, and Woodward's case of the gauge sigma model. That's a kind of diabatic approach. And I think Wilhelm and Woodward and Wilhelm and Salomon studied this kind of things for a long time using that kind of approach. But we try to kind of bypass this analytic problem using more on this kind of infinity technology. And that's the approach we are working on to attack this kind of conjectures. Okay, so now I want to rather brief on this because I don't know so much well about this. But this story of correspondence should be related to this story of micro-local support of the sheaf, which I want to say a few words. So Kashiwara-Shapira, if you have a sheaf on a manifold, then they say that there is a singular support of the sheaf. It's a kind of conical subspace of the conical means that R plus invariant Lagrangian submanifold on this cotangent bundle. It could be singular. But then in a typical case is the following. So suppose we consider the case when this Lagrangian submanifold came from generating functions by f. They have an extra y parameter. Then you consider this u of f. So x is an Rn, y Rm. Then we take another thing so that lambda is bigger than f of xy. So you have some open set on this big space. Then you take this uf and you take a sheaf which is 1 on this uf and 0 outside. And then there is a trick called this trick is based on tamarking. I don't want to explain so much, but the point is that this singular support is actually conical. You consider only R plus invariant Lagrangians. But Tamarki and those people gave a trick. If you increase one dimension so that conical thing is just the usual things. So that is what is LF hat. And then Lagrangian submanifold in the cotangent boundary of M is Lagrangian submanifold of this M cross R, which is invariant under R star actions. This is a kind of approach go back to Tamarkin. And he want to use it to study simplex geometry of Lagrangian submanifold of cotangent bundle. And he gave first example to prove some non-trivial theorems without using the pseudo-harmonic curve. And after that, Kashiwara-Shapira and Gilmore and several people coming again. This approach is getting more interesting. So now what is expected is that the Frey homology of L is supposed to be a sheaf homology on this sheaf, which correspond to these things. So now, so this is these people. It is very incomplete list. Maybe 10 years ago, this area was not just the beginning, but after 10 years, it is getting very interesting areas, and many people come to be involved in many works. So I can just start learning a bit after doing this generating function things. So I cannot say so many, but there are many people working on this. And then I think the question people not yet so much study is that this functoriality are related to this correspondence between Lagrangian submanifold and the sheaf theory. So Lagrangian submanifold side, you have this Frey theory, and you have this infinity functors. And the sheaf theory side, actually composition of the sheaves and its micro-local support is very much a classical area. I think this Kashiwara-Shapira's work came from this from the earlier work on the D modules and the quantized contact transforms. And it's a differential equations, and the composition is very much from the beginning. And I really want to understand that how this Lagrangian correspondence and its compositions are related to this sheaf and its compositions by this Lagrangian sheaf correspondence. And so far, I don't know so many people discussing it. Probably the area is rather far away, and there is not so many people who understand these two fields. I mean, Lagrangian correspondence and its Frey theory, and this difficult story of this micro-local sheaves. To understand both is not so much easy task, and not so many people understand it. And I don't understand the sheaf side enough. So probably in the near future, somebody is coming and to make it more. And I expect, because the composition of a sheaf is very much important for D modules and those things. And so I want to really use this Lagrangian correspondence things that are related to this issue. And maybe I have just a very few words. And another thing is something like a tensor product of Lagrangian submanifold. And there is a symplectic manifold, and there is some notion called SYG relations. It is called a fiber bundle, and whose fiber is a Lagrangian tori. And it is related to mirror symmetry. And the conjecture, I don't know who first did it, in this kind of situations, this category of M has a structure of tensor product. You know, here you go to the mirrors, you have a category of derived category of sheaves, and you have a two sheaves, you can tensor product. And this structure is not missing, you just consider symplectic manifold. You have two Lagrangian submanifold. How to construct tensor product of Lagrangian submanifold is very much mysterious. But in the case when this SYG fibrilation exists, there is a natural way. So in the simplest case, if M is a cotangent bundle, then you have a graph of D of F and a graph of D of G. The tensor product is actually sum D of F plus G. And in a more general case, that in a fiber is a toroid. So the toroid has a structure of abelian group. So you have a two Lagrangian submanifold. You can take fiber as sum of this two Lagrangian submanifold. And that process is expected to give a tensor product. And one can see that if everything is regular fiber, then the sum is actually again Lagrangians. And there are people, there are young guy called Sbornik, a student of Duniuru who wrote a thesis in more than 10 years ago or something, who realized this kind of project in the case of 2n and linear Lagrangian submanifold. But now there are Symplectic. And now that we are now becoming again a bit more serious, and Asahi Botman and this is my new student in Stony Brook in Penn are doing this kind of things, at least in the case of K3 surface. I think they will soon finish these cases. And I believe this should be in complete generality. So for any SYG fibrillations, this category has a tensor product structures, which is actually mirror to the tensor product structure of this. And why I say so is that because this functor is expected to come from some Lagrangian correspondence between M cross M and M. So there is a candidate of this tensor. So using this correspondence things, we can study these problems. Okay, I stop here. Thank you very much.
Questions?
I'm studying algebraic topology, a lot of study symplectic geometry. I have a basic question about the Lagrangian correspondence. You have the correspondence for a map of symplectic manifolds M to N corresponding to a Lagrangian submanifold of the minus M times N. So you also define a fiber product for two Lagrangian submanifolds. So by using the Lagrangian correspondence to the composition, you means so when M equals N, it makes sense for the composition. I think the correspondence should be correspond a product for two symplectic morphisms from M to N. So
I mean,
you can give a explicit description for the when M not equals N, we have define a certain composition or product.
I think you just consider the case of symplectic diffeomorphism. The story is not just a composition of the symplectic diffeomorphism. It's not new. But even in the case of M and M, you may have some Lagrangian submanifold, which is somehow related to similar to Lagrangian diffeomorphism, but it's not actually Lagrangian diffeomorphism. So you can compose it. One possible interesting thing is that kind of studying the composition of many time composition of symplectic diffeomorphism is a very fundamental problem with symplectic geometry and Hamilton dynamics. So we can try to generalize Hamilton dynamics for symplectic map, Lagrangian correspondence, which is not symplectic map, but it's just this kind of correspondence.
Okay, thanks.
More questions? One by one.
Is there also a mirror symmetry between symplectic topologism and complex topologism?
Pardon?
Symplectic topologism and complex topologism, is there also a mirror symmetry between them?
I think what is expected is mirror to symplectic topologism is symplectic topologism group, Lagrangian topologism group is something like an algebraic K group. Complex topologism, I don't know. Maybe complex topologism is rather novel notions, which is not so much, I don't know so much. But it's about, I don't say about symplectic topologism, it's about Lagrangian cobordism. That's very popular notions. So you have Lagrangian submanifold correspond to sheaf. Then cobordism is finer relations, finer conditions than kind of give the same homology class or some isomorphic object. And then in the derived category object, it gets a bit more information and kind of, algebraic K has begun. That's something expected, but I don't know how much it is. No, several people study, but not so much yet successful.
Thank you.
Thank you. So in the mirror symmetry, so what's the corresponding element of the bounding cochain in the other side, in the sheaf?
What one can say is that if there is no bounding cochain, there is no sheaf, which is mirror to it. So the issue is that Lagrangian-Floer theory, it is usually something obstructed. And complex geometry, it is rarely obstructed. So that, but there are some cases, so here consider the deformation theory of sheaves in complex side. Yeah. Then in many cases, it is just not obstructed. H1 is a deformation parameter. But in general, you have some H2 and you have some map. And then you have deformation theory. And this deformation theory corresponds to the symplectic side, deformation theory of this bounding constraint.
Okay, thank you.
Actually, there is a question. It says, what is the candidate Lagrangian correspondence M times M to M?
Okay, so you take a base space B, X in B. I'm not so much sure whether this works again. I was, yeah. Yeah, it works great. So I think you take this M to B. Then you take X, Y, Z, M cube, and pi X, pi Y, pi Z is B, and Z is X plus Y. So fiber had a good start. So you take this subset, and you can think that the dimension is correct, and in a good way, it's around someone.
More questions? So let me ask you a question. Long time ago, of course, Fukaya category was very famous and still is. And I remember one of the most insightful texts I read about your category was this long draft of Diniuro, who starts with Morse homology on infinite dimensional manifolds and basically tries to describe symplectic floor homology. So I'm asking this because it helped me back then understand it. So maybe can you, in that picture that you have two Lagrangians, if I think that there is a Morse map between from one to the other, whose critical points are those points of intersection, can you explain why? Obviously, I have a map from one Lagrangian L1 to L2. I can think of this continuing and giving me a cochain complex of these Lagrangians. And at each degree, I can calculate cohomology or homology. Why is this the quantum cohomology where you just get by taking homology of your manifold, twisting it by Novikov ring? Is there a fast way of saying
I think, so what's is the quantum cohomology? Then cohomology group, the additive group does not change. Only the ring structure changes.
Yeah.
And the Floer homology, the Lagrangian intersection is just an intersection point. But the Floer homology can be smaller. It means that the boundary of already additive group changes. The reason is dimension counting, because in a case of so-called closed strings, your Riemann surface has S2, and then they have marked points, and everything is even dimensional. And in our case, you have this disk, and there are some moduli space of odd dimensions. So this odd dimensional moduli space is responsible to deform homology group also. So my impression is that the homology group does not change, is rather accidental.
I see. So if I used this Morse map, look at the chains I get at each level, I calculate cohomology. It is natural to expect that at each level, the cohomologies will have holomorphic disks counting in them too.
I mean, you have two different critical points.
Yeah.
Usually Morse boundary map. is collected using holomorphic disk. That's a general picture.
Okay, so you take it and then correct.
Yeah.
Okay.
Maybe a quick comment. So yeah, so there's also the third directions, like this homological mirror symmetry, compare Fukaya with the coherent sheaves. You can also study category of representations of certain algebra that obtained from quantization of the space of which you're studying the symplectic homology. And then it's kind of this new program, which is pushed by Kontsevich and Sobliman, and also did some work on that. So do you know, can you comment on representation category at all? Or
I don't know so many about it. But I think to make this algebraic thing of representation category, usual way is to find some kind of generator of this infinity category. Then in place of taking all the Lagrangian sum manifold, you can just take this generator, right, and all unknown Lagrangian sum manifold just correspond to the module over the smaller infinity.
That's correct. Yes, well, the compact Lagrangian corresponds to finite dimensional representations, and non-compact to the infinite. Yeah, sort of. Do you have a hope that this functoriality will persist there, or is it not clear?
I mean, because the generator may not correspond, but if you want to calculate this kind of functor,
right,
you can just calculate for the generators.
Well, so just have example in SL2. So, but yeah, like
yeah.
More questions? Okay, if not, let's thank Kenji again. If you haven't put your names in here, these are still here. So yeah.